Hello everybody, and welcome to the beginning of page 129 in the workbook. In this definition, we are going to define what we mean by orthogonality and length in an arbitrary inner product space. Okay, so we will assume that we have an inner product space over a field, and again, that could represent the real or the complex numbers. And here's how we're going to define orthogonal. Two vectors x and y we'll call orthogonal if their inner product is equal to 0. Okay, and then we define something called the norm, which you can think of as a length, to be the norm of x, that's the way that we would read this symbol, is equal to the square root of the inner product of x with itself. Okay, now, just to give you an idea of why we might make those definitions, let's look at a familiar example here. So R2 with the standard inner product. Remember again, that's just the dot product. Okay, I want to invent two vectors here and just take their dot product, just to give you an example. So what if we took the dot product of 3, 1 with negative 1, 3? Okay, well by definition, that's just 3 times negative 1 plus 1 times 3. That's equal to 0, and so this calculation confirms that those two vectors are orthogonal. Okay, and you could see that if you just sketched a brief graph here. So 3, 1, okay, is this vector, and negative 1, 3 kind of looks like that. Okay, and you can see that we've kind of got a 90-degree angle between those vectors. Okay, and we could, let's test out our definition of the norm. So the norm of these two vectors, or actually the norm of one vector, let's just pick one of them, 3, 1. Okay, according to our definition, that would be the square root of the inner product of 3, 1 with itself. Okay, and so that would be the square root of 3 squared plus 1 squared, which is the square root of 10. And that turns out just to be the length of that vector, the normal Euclidean length that you calculated in a calculus course. Okay, so the two definitions that we have up here just generalize those two notions to an arbitrary vector space, or an arbitrary inner product space.